Hello everybody and welcome back to another Calculus 2 video. Now we will talk about finding the maximum and the minimum values of a function. So by extreme, I mean the highest and the smallest values of the function. So if you remember in Calculus 1, how did we find the maximum and the minimum value of a function? We were looking at, if you look at the graph of a function, then over here we have a local maximum and over here we have the local minimum. And what was so special about these 2 points? The slope of the graph is 0, right? So in order to find these points, we had to find where the derivative is 0. And we called these points the critical points. Once you find the critical point, then what did we do? We used the second derivative test. And so this one was the critical point. And then the second derivative test, you look at the second derivative, you plug in the critical point, and if the second derivative was positive, right, that means that the function is concave up, right? So the function shape is like this. And if the function shape is like this, that means that the critical point will be a minimum, right? So this is a minimum. So if this is positive, then you get a minimum. And likewise, if the second derivative of the critical point was negative, it means that the second derivative, well, the graph is concave down, so the shape of the graph is like that. And if the shape of the graph is like that, then you're dealing with a maximum value. And this intuition basically translates to a function of 2 variables. The steps of finding the maximum and minimum values of a function of 2 variables are pretty much the same as here. So what do we do? To find the max mean values of a function of 2 variables, this is what you do. First step, you need to find the critical points. So instead of setting f prime equal to 0, for this we have to set the partial derivative with respect to x equal to 0 and partial derivative with respect to y also equal to 0. And you're going to get an equation from here, you're going to get another equation from here, and you solve these as a system of equations simultaneously. After you find the critical point, you perform the second derivative test. Which is the following. You calculate this complicated looking, but in fact very simple quantity. So you take the second derivative with respect to x, multiply it by the second derivative with respect to y, and then you subtract, this guy squared. Now, what can happen is that this quantity, when you calculate it, it can be either negative, in which case we call our critical point a saddle point. A saddle point. So a saddle point is a point that's like neither maximum nor a minimum. In Calculus 1, we have a function like that. If you look at the graph of x cubed, then here, this would be a critical point, but it's not a maximum and it's not a minimum. We call this a saddle point. So that's what saddle point is. It's a critical point, but it's neither maximum nor minimum. It can happen sometime. If this expression is positive, so let's say you calculate this and you get 10, right? Then what happens is you have to then check out fxx. Now, if this guy is positive, then we're dealing with a local minimum, and if this guy is negative, then we're dealing with a maximum. Okay? And that really is just like calculus 1. Now let me do a couple examples to show you how it all works. Let's take this very simple function. And let's go through the algorithm to find the extreme values of this function. So first, we have to find the critical points. So the rule is you take the partial with respect to x equal to 0 and partial with respect to y equal to 0. Partial with respect to x here would be 2x, set it equal to 0, x equals 0. Partial with respect to y, this is 2y, set it equal to 0, you get y equals 0. So our critical point is 0, 0. This is our critical point. Kind of looks like an owl. Second, let's carry out our second derivative test. So what we do is we calculate this expression. Right? What's the second derivative with respect to x? Well, the first derivative was 2x. If I take another derivative with respect to x, this becomes 2, right? Maybe I can write my answers below the expression. So the second derivative would be 2. The second derivative with respect to y, well, let's see. This is the first derivative with respect to y. If I take the derivative again, this becomes 2. For this one, I take the derivative with respect to x first. I will get 2x. And then I will do with respect to y next. Well, with respect to y, this becomes 0. So you get 0 squared. So our answer is 4. Okay? So that means that this expression is positive. We kind of have to move to the left of this diagram. And when I move to the left, I have to, it tells me to check fxx. Well, if I check fxx, okay, again, remember, it was 2, right? It was 2. And so this is positive, and if this guy is positive, then we're dealing with a minimum value. So this is a local minimum. And indeed, if you remember, we talked about the graph of this function. The graph of the function is a ball, and you can see that at 0, 0, the function has a local minimum. Right? Let's look at another example. Okay. All right, so let's look at the function 3y squared minus 2y cubed minus 3x squared. Okay? So, first step, we must find the critical points. This is the rule. If I take the partial with respect to x, what do I get? 0, 0, negative 6x, and here I get what? Plus 6y, right? Make that equal to 0. And then with respect to y, I get 6y, I get negative 6y squared, 0, and this becomes 6x. So I have two equations which I have to solve simultaneously. It's a little bit different than the previous example where it worked out independently. We didn't have to solve anything simultaneously. Here we have to solve it simultaneously. So I'm going to use the substitution method. From this one, you can show that x has to be equal to y, right? So I can substitute, instead of x, I can put y in here. So this becomes 6y squared, and here I put y. Maybe I should explain this. how do I get this? Well, from here, what do? Negative 6x equals, move this to the other side, and divide both sides by negative 6. Okay, let's go back here. So I substitute instead of x, I put y. And now, what happens? I get 12y minus 6y squared equals 0. Take 6y out, you get 2 minus y equals 0. So this gives us y equals 0, and this guy gives us y equals 2. And notice that x has to be equal to y. So if y equals 0, x is 0, and if y equals 2, x equals 2. This is our first critical point. This is our second critical point. And our second step is to apply the second derivative test. Let's apply it to the first critical point, 0, 0. Okay, so remember what we have to calculate is this guy. So the second derivative with respect to x. This was the first derivative with respect to x. If I take another derivative with respect to x, this becomes negative 6. This was with respect to y. If I do another time with respect to y, I get 6 minus 12y, and this is 0. And then over here, what I have to do is I have to take with respect to x, which is here, and then take with respect to y, and that will give me 6. Now, over here, we have 6 minus 12y. If I have to plug this point in here, and if I plug in 0, 0 in here, this becomes 0. So all you have left is with 6. 6 times negative 6 is negative 36. Minus 36. Negative 72. So this value is negative now, it turns out. And if you remember, according to our diagram, we conclude that 0, 0 is a saddle point. I'm going kind of fast, but I hope you guys are able to follow me. And then, real quick, let's check the second critical point, 2, 2. Again, we have to take the second derivative with respect to x. It was negative 6. Second derivative with respect to y. And this guy, it all stays the same. Now, if I plug in 2, 2 in here, what happens? When I plug in 2 in here, this becomes negative 24 with plus 6, negative 18. Negative 18 times 6, I think it's 108 minus 36. So that gives us 72. Okay, so we get a positive answer. And so that means that in our diagram that I drew before, we move left. And if I move left, I have to look at fxx. And what is this equal to? This is equal to negative 6. And remember, when this guy is negative, so when this guy is negative, our conclusion is that the critical point is a local, what? Maximum, right? So go back to the diagram and make sure you understand the steps. And we're done.